All right, everybody. We are going to start our new chapter on 2.1 function families, and we're focusing more on like linear things and polynomials. That really is where we're getting into. So, when it comes to different types of functions, you're going to see different types called of power functions, and we're going to focus there first, okay? Not the only types of functions that exist, but that's where we're beginning. So power functions are the types of functions that where you have x and then it's raised to a particular power. Like here in your examples, we have x to the second power, x to the third power. Here, technically a square root function is a power function because it is raised to the 1/2 power. All of those are power functions, okay? Now, let's get a little bit more specific. A monomial function, mono means one, right? So when I talk about a monomial function, we're talking about a function that has one term, such as this. We only see one value, one term. Now, it is a type of power function, but it's more specific. So if you look here, a very important feature is that your exponent in it is going to be a positive integer. That's different than what we had on the power functions because it didn't matter. As long as it was a number, it didn't matter. But on the monomial function, we want only positive integers. Okay, so the square root function would not count as a monomial function because this has a 1/2 power. That's not an integer. So remember, integers are like whole values. They're not fractions. They're not decimals. Integers can be negative, 0, positive, whole values. Okay. I only want positive integers. So that's like 0, that should be like 1, 2, 3, 4. Okay. Positive integers. Basically, whole numbers. All right. Polynomial functions. This is where things get a little bit more interesting. Poly meaning many. We have many terms. That's what it boils down to. It's very similar to the monomial function in some of those properties. However, there is more than one term. Okay. We're going to start off with a large exponent and then we work our way down. So in standard form, we would put it to where the highest exponent is first, and then it is in decreasing order. So pretend that this first one was to the 5th power. The next one would be to the 4th power, 3rd power, until you run out and it becomes a constant at the very, very end. Now, in here, we're going to look at making sure that if it's a polynomial function, these are things that are going to be true. Your exponent n is going to need to be a non-negative integer, meaning it could be 0 or it could be positive. And it can be an integer, meaning whole values. It's not going to be negative, okay? Non-negative whole numbers, right? So we don't want any decimals, no fractions, and we need it to be positive or 0 is okay. Okay, each coefficient is real, so we don't want any imaginary numbers, right? Okay, so let's try a few problems. Okay, if you need to pause the video and write anything down, feel free to do that. Rewind, whatever you need. But we're going to go through this little example here first, and then I will probably make a separate video to talk about the next topic because the next topic is kind of sort of different. Like it kind of goes along these lines, but it branches out in a different way. So we're going to go through this example and then we'll probably pause it and do a second video for the second part. All right, so here we are. Is it a polynomial function? If yes, we're going to state the degree and the leading coefficient. If not, then we have to explain. Okay, so I'm going to try to keep the definition of polynomial function up there. So for A, when we answer this one, right, we have this lovely little function that they've given us. And what I want to look for is the exponents, right? Are my exponents non-negative integers? Well, my exponent on the first term is a 3. The exponent on the next number is a 1. And the exponent on this one technically has like an x to the 0 power, which is 1, so you don't see it. Okay? So an exponent of 3 1, and 0. Those are all non-negative integers, so that's fine. Each coefficient is real. We don't have any imaginary numbers. So yes, we would say that this is a polynomial function. They ask us to give the degree, which the degree is going to be the highest exponent that you see, 3. And then the leading coefficient. The leading coefficient is going to be the coefficient in front of that first term in standard form. So look at the one with the highest exponent. The number in front of that is your leading coefficient. That would be a 4. Done. All right, here we go with B. This time we see a function 6x to the negative 4th plus 7. So we're asking, are all of the exponents non-negative integers? No. Negative 4, that's not non-negative. Wow, that's a lot of not nons. Anyways, this is a negative number. So it does not fit that category where we have to have non-negatives, right? So we're going to say this is not a polynomial function. Okay. The reason it's not a polynomial function is because that negative 4 and we can't have negative exponents. We can't have a negative exponent for any of my exponents on a polynomial function. Okay? All right, let's look at C. All right? C is a little bit of a trickier type of question. So I want to look at this for a second. I know a lot of people have been having questions about it, and it was honestly sparking more debate in class than I thought it would when we've gone over this. But to be able to tell me if this is a polynomial function or not, we need to really know what's going on with that square root. And remember how we talked about, even at the beginning, I said that a square root function is a power function because it is the same as having a power of 1/2. So I could rewrite this guy technically as to the 1/2 power. That means the exact same thing. So if you wanted to rewrite it that way, you could. A lot of people stop here and they say there's a 1/2 exponent, and that means that it can't be a polynomial function. Okay? I also want you to look a little bit deeper at it because some people today have been asking me, or in class, they were asking, what if I square root that 9 though? Because 9 is a perfect square. X to the 4th is a perfect square. 16 is a perfect square. X squared is a perfect square. Why can't we just square root all of it and then we wouldn't have that anymore? Or you could think of, they're looking at it, what if I just distributed that 1/2 exponent to each of these terms? And here's what I brought up, okay? Go to a completely unrelated thing, but it'll relate in a second. What if I was asking you guys about something like this? Okay? Is this the same as x squared plus 2 squared? X squared plus 4? No. This guy is not the same as x squared plus 2 squared. This does not distribute through. You cannot do that. What this is the same as would be x plus 2 times x plus 2, completely different. You cannot just distribute this exponent to these because of that plus symbol. Okay? If they were multiplied, then that power does distribute and go to both of them. But because these are being added, it doesn't work that way. So bring that back to the question we were working on. A lot of people said, can't I just take this 1/2 and I distribute it to each term? No, we cannot. If you did, it would be wrong. It does not work that way, just like it didn't work that way with the other one, right? Because of that plus symbol, we cannot just simply distribute that power. It doesn't work. So what we have to think of instead is, you could try to factor out an x squared, but really there's not going to be a good way for this to simplify. And with that being the case, that brings us back to the fact this is a fractional exponent. If you have something that's a non-integer, it's not going to be a polynomial function. This is not an integer, so this is not a polynomial function, okay? 1/2 exponent is not an integer. Okay, if I could spell, that would be cool. All right, last one. This one should be easier, okay? D. We're looking at this guy. Look at your exponents. The exponent on this first one is a little invisible 1. The exponent on the other one is a 4. Those are both non-negative integers. We're solid, okay? I don't have any imaginary numbers. We're looking good. I would say, yes, this is a polynomial function. And we need to then list the degree. Remember that the degree is the highest degree that you see, which is a 4. And then the leading coefficient should be the number in front of that term, okay? Now, a lot of times they're trying to trick you on this one by trying to make you pick 15 to be your leading coefficient, but this is not in standard form. This guy would be better written if I did k of x, and if I actually put it in standard form, it would look like this. That leading coefficient is a -2 because that is the coefficient to your highest exponent term. Okay? So we're going to stop this one here. I know this is a little bit of a shorter video. We're going to stop this one here. And in the next video, we're going to talk about the average rate of change. And that one will be a little bit more lengthy because we've got a few more examples on that. Okay? I will see y'all in the next video. Bye.